All right, so let's talk about the general shape of polynomials. And on this slide here, you see the first four degrees of first, second, third, fourth degree polynomial. And what we're focusing on here is the number of intercepts. So the number of intercepts is at most equal to the degree. Okay, so a third degree polynomial can have at most three. When I say intercepts, I'm specifically means x-intercepts. Okay, so I should be careful about that. These are zeros. The number for a third degree is 3. The number of fourth degree is 4, and so on. So you might not have that many, but at most you can have equal to the degree of the polynomial is the number of x-intercepts. Okay, what about turning points? What about turning points? Well, the number of turning points is always going to be 1, and again, this is the possible number is going to be equal to the degree of the polynomial minus 1. So for a first degree, we have 0 turning points. A second degree, we have 1. Third degree, 2. Fourth degree, 3. So at most, n minus 1 for an n degree polynomial. For inflection points, and again, I should say possible number of inflection points. And remember, inflection points are changes in concavity. So the possible number of inflection points is going to be equal to the degree minus 2. Now, there's a little problem here because this doesn't work for linear. Linear have none, but so this formula only works for quadratic and higher. So degree 2 and higher. So for quadratic you have 0, linear you have 0, but for a cubic you have 1. For a quartic, you have 2. So if we just kind of talk about this in general, all nth degree, so n is being some integer, 1, 2, 3, 4, 5, 6, 7, whatever, all of them have all real numbers as their domain. N x-intercepts, or real number zeros, at most, and at most n minus 1 turning points, and at most n minus 2 inflection points. So if I have a 17th degree polynomial, it can have at most 17 zeros or x-intercepts, at most 16 turning points, and at most 15 inflection points. All right, so continuing our classification, we're now going to look at things in terms of evenness and oddness, and as well as the sign of the leading coefficient. So we'll begin by looking at odd polynomials whose leading coefficient is positive. So when I say odd, I mean the degree of the polynomial is odd. So 1, 3, 5, 7, etc. And that's the power of the highest polynomial in the polynomial is odd. So that would include our linears and our cubics. And the fact that the leading coefficient is positive, well, let's look at how that affects things. First of all, what about the range? The range is going to be all real numbers. Okay. What about the kind of endpoint behavior? So on the far left-hand side, so when I say far left-hand side, you want to think about this as over here, we're over at negative infinity. That's the left-hand side, positive infinity on the x-axis, and here we have infinity and negative infinity on the y-axis. Okay. So on the far left-hand side, as we are over here, outputs increase from negative infinity. So we're moving from left to right. So as you move from left to right, you're basically going to be coming up from negative infinity and concave down. Okay, as long as it's not linear. Now I know that arrow is pointing down, but we're still moving from left to right. So on the far right hand side, so basically over here, we're basically going up. So I guess the general idea here is that the overall qualitative behavior is upwards from negative infinity, and then maybe a bunch of bends or whatever, but then up again. And the number of bends is going to increase as the degree of the polynomial increases. But overall, this thing is sloping upwards. Okay. Now, if we change that leading coefficient to negative, but we keep it as an odd degree, then basically just the overall behavior is overall downwards. Right, so again, our range is all real numbers, but here on the far left-hand side, outputs decrease from infinity, and the graph is concave up in this case. And on the far right-hand side, outputs decrease to infinity. I'm sorry, hold on. That should say negative infinity. And the graph is concave down if n is not equal to 1. So there's a little mistake there. Okay. Now, if we look at even degree polynomials, the situation is quite a bit different. So let's look at even degree with positive leading coefficient. So second degree, fourth degree, and so on and so forth, where the a value is greater than 0. So in that case, we kind of have this overall concave up sort of thing. Trying to write legibly. Overall concave up. Now that doesn't, when I say overall, I mean that that doesn't mean it can't be concave down, like that's concave down right there, that's concave down, but overall this thing sort of cups upwards. So the way that we capture that is by saying this, as we move from negative infinity left to right, the function is going to be decreasing from infinity, and as we move towards positive infinity from left to right, the function is going to be increasing towards positive infinity. Okay. Now if we look at even degree polynomials with a negative leading coefficient, as you might expect, we basically just flip things upside down. Oh, and you know what? I kind of skipped a bunch of stuff there, but I'm sorry. I should talk about ranges and stuff. So let me mention that. So for going backwards, and my apologies, for a positive leading coefficient, it does have a minimum value. So for the odd degrees, we don't have a minimum value or a maximum because they just go up and down. But for the even degree leading coefficient positive, we have a minimum value. We do have a bottom, and then we go up from there. So that means we have a minimum value k, and then our range is going to be limited by that, from that minimum value upwards to positive infinity. Now for a negative leading coefficient, but also even degree, we have a top for these. So they all have tops, and then they go down from there. So the range is going to be negative infinity up to k, where k is the maximum value. Okay. And as far as the overall behavior, these guys are kind of overall concave down. Now, again, that doesn't mean that there aren't portions where it's concave up. That's concave up. That's concave up. That's concave up there and there. But overall, the thing bends downwards. And that's for even degree negative leading coefficient. Okay.